All right. So for these, we have to look at the molecules, figure out if the bonds are polar or nonpolar, and then if the molecule overall is polar or nonpolar. Something we practiced a little bit in class. So the first one, it's easier actually to look at the bonds first. This only contains one kind of bond, an NF bond. So that will either be polar or nonpolar. What do you think? Polar, yeah, and the chart here tells you. So that means that this one has polar bonds. Now, is the overall molecule going to be polar? Yes, because all of the more electronegative fluorines are on the bottom, the less electronegative nitrogen's on the top. So we have a negative on the bottom and a positive on the top, and that makes a polar molecule. All right, what about formaldehyde? Does it have any polar bonds? What's a polar bond? Right, the CO is a polar bond because there's a significant difference in electronegativity between those two. Does it have any nonpolar bonds? Yeah, the CH bonds are what we consider nonpolar, very small difference in electronegativity. So that one has both kinds. And then overall, is this molecule polar or nonpolar? Right, this is going to be polar. Now, a totally symmetric molecule like that, if there were oxygens on all three sides, that would be nonpolar because all the three polarities would cancel each other out. But because two of them are hydrogen, and that's not polar, that doesn't really count. So all the positive is down near the bottom, and the negative is up at the top. So that's a polar molecule as well. That's formaldehyde. And then nitrogen, N2, does that have polar or nonpolar bonds, or both? Nonpolar bonds. There's no difference in electronegativity between nitrogen and nitrogen. They're the same thing. So that those would be equally shared. And then the molecule must also be nonpolar because that's the only bond in there. So. All right, hopefully that was good. And then some names. Write the formula or give the name for the following. Tin 2 carbonate. So hopefully you've gotten a chance to practice this a little bit more. Tin 2 means SN2+. And then carbonate, we know from the list, is CO3 2-. So we have 2+ and 2-. We just stick them together. We don't need to adjust the ratios there. So the formula is SnCO3. All right. PF5, phosphorus and fluorine are both on that side of the staircase. So that means this is a covalent or molecular compound. That means the other style of naming where we specify how many of each thing there is. And so this one becomes phosphorus pentafluoride, like that. And finally, magnesium nitride. Magnesium is Mg2+. We know it's 2+ because it's in the second column, group 2A. And then nitride is N3-. And we've practiced this a little bit. To get the 2+ and the 3- to balance out, we need 3 of the 2+ and 2 of the 3-. So that compound will end up being Mg3N2. Does this go okay? Maybe? Okay. Keep working on that. As you saw with the equations, that's going to keep coming up. It's going to be on the next quiz. It's going to be on the quiz after that. It's going to be on the next exam. So keep working on these things, please. And then finally, what is the type of attractive force that occurs between iodine molecules? So an iodine molecule, I didn't ask for the structure here, but an iodine molecule looks like this. What kind of a bond is that? Polar or nonpolar? Yeah, that's a nonpolar bond. So that means the only types of forces are the dispersion forces, right? Nonpolar molecules have dispersion forces. And the ones in iodine are actually pretty strong. Iodine's a solid at room temperature because the iodine atoms are so big. All right, so that was the quiz. Any questions, problems? Okay, let's move on. last time we looked at some chemical equations. In lab tomorrow, we're going to do these different reactions. We're going to do different types of chemical reactions and practice the equations. So that should give you some good practice going in for the quiz next week. One thing I want to add that we didn't talk about, we kind of mentioned it at the end, but we should probably talk about it formally. We looked at these 4 different types of reactions: combination, decomposition, replacement, so single replacement and double replacement. I want to add one more to the list. I'll just kind of squeeze it in here so they're all in the same place. And that is combustion. Combustion has various definitions, but the one that we're going to focus on here is simply the addition of oxygen. So the reaction with oxygen. And primarily we're going to look at hydrocarbons. So things like methane reacts with oxygen. This thing's going a little crazy again. I don't know if it's the pen or... Methane reacts with oxygen to make carbon dioxide and water. And in general, the reaction is going to look just like this. The only thing that's really going to change is instead of CH4, it might be some other CN something. There could even be some oxygen in there too. That thing could change. Everything else stays the same. It reacts with oxygen and forms carbon dioxide and water. We call that a combustion reaction. Now this one isn't balanced, so we should balance it. To do that, go here. And in this type of combustion, this is always what we're going to form. We will always form carbon dioxide and water as products. So that's a pretty easy one to spot and to know about what's happening because it's pretty specific. You might say that like this is a form of combustion, magnesium plus oxygen, so that kind of makes sense also. You'll see we're going to do this reaction in lab tomorrow, and it's a pretty it releases a lot of heat, a lot of light, it burns, it like really burns brightly. So that kind of says combustion sometimes. And so that kind of fits in this category, but the way the book defines it, the way we'll kind of narrowly define it is just this way, looking at hydrocarbons reacting with oxygen. All right. Okay, hopefully you had some chance to practice balancing equations and that kind of thing. Today we're going to look at adding in some calculations. That is, how do we figure out how much of one reactant we need if we want to actually set up a chemical reaction. And to do that, we need a new concept. Might not be new to all of you, but to some of you, the mole. Have you heard of the mole before? Anybody done stuff with the mole before? Maybe. Seen it? Yeah. So what is it? You know? Why is it useful? Okay, then let's look at it. The mole is it's actually kind of a simple thing just on its face. It's just a quantity. It's a word that's used to describe a number. So a quantity. In this case, the quantity is a very, very large number. Oops. 6.02 times 10 to the 23rd. Exceedingly large number, an unimaginably large number. If we were to write this all out, for those of you who don't like scientific notation, looks like this. That number is so big, we don't really know what to do with it. I mean, on a kind of philosophical scale, we have no sense of what that means. We can't even really imagine like a million or a billion. That's kind of beyond our scope, and this is now way, way bigger than that. So in any practical, from any practical standpoint of like what we see all the time, this number has no meaning. And so what do you think it's used for? Where could a number this big actually be useful? Yeah, if you're counting really, really small things, then you need a number that's this big. If the things that you're counting are so unimaginably small that you can't even see them and you can't even count them, then you need a number like this to bring them up onto our scale. And so that's what this number does. The thing that, or where this number comes from, one mole of carbon atoms. So that number of carbon atoms, if you had that many of them, you could count them out and put them somewhere. Weighs 12.011 grams. So that's how we translate from the atomic scale, which is so small we can't deal with it, to our scale. If you have 1 mole of carbon atoms, it weighs about 12 grams. 12 grams is a reasonable amount. That's a small, kind of a palm full of carbon. We could weigh that out in the lab. It'll be fine. One of the biggest points of confusion with the mole is thinking of it as a unit. It's not really a unit because it's not a measurement. It's a quantity. It's how many of these things are there. There are other words that we use that refer to quantities. Anybody know some of them? Let's put some others up here because they are the same type of a thing. What's another word that we use to refer to a quantity? Anybody know one? Oh, sorry, I'll just tell you. If I can write it without this thing freaking out. A dozen? How many is a dozen? 12, yeah. So that's the same as the mole. It's a word that means a number. It means a quantity. If you have a dozen donuts, you have 12 donuts. Anybody ever eat a dozen donuts at once? We should try it. Yeah? Okay, so you have a similar word. Do you guys like donuts? Do we have donuts someday? Would you eat the donuts? Last semester one time, I had a bigger class, and I brought in donuts, and everybody was like, no, we don't really eat donuts. Like they were unhealthy or something. So I had a bunch of leftover donuts. So that day, I didn't want to buy more food, so I only ate donuts. That was not a great decision. But I think I made it through like 9. That's a lot of donuts for a day. I didn't feel great. It's all right. So if I bring in some donuts, you'll eat them? All right, then we should have some donuts. But don't leave me with 9 donuts, because otherwise I'll eat them. Feel terrible. Okay, anyway, there's another number. There's some other ones that you may not know as much. Gross is 144. That's a dozen. 12 times 12. So if you're shipping things or packing things, you might have a gross of something in a big box, like pencils or something. I don't know. But that's just to give you an idea of what this number is. It's not a unit. It's not a measurement. It's a number. It's a quantity. It's a count. It's how do we count things that are very, very small. So just like you would if you had a bunch of boxes of donuts stacked up, you could count the donuts in dozens instead of having to count the individual donuts. You could say, okay, this is 10 dozen donuts, 10 dozens of donuts. And then you could do some math and figure out that that's 120 donuts. And we can do the same thing with atoms. We can say we have a mole of carbon atoms. And then we don't have to count and say that we have 602 whatever bajillion carbon atoms. We just say we have a mole of them, and then we can count them that way. So when we deal with chemical quantities, we're going to deal in moles, because that's a way that we can actually measure and we can actually count them rather than individual atoms. So if we go all the way back up here to our first reaction that we looked at, this hydrogen reacting with oxygen to make water, the reason we have to deal with these moles is because in a chemical reaction, molecules react with molecules by a count. So we said 2 of those reacts with 1 of those to make 2 of those. We didn't say 2 grams of this reacts with 1 gram of this to make 2 grams of that. That doesn't work. It's the count that happens. It's like how many of these reacts with how many of these. So we have to use that mole idea to get back and forth between what we can measure, which is like grams, and what we can count, which is individual molecules or moles of molecules. So let's take a look at what that looks like. This statement here, I think I figured it out. It's a pen. I hold it just right. I think I can stop it from doing that. I don't know. 1 mole of carbon atoms. So that statement can be expressed as an equality one mole C equals 12.011 grams of carbon. And once we have an equality like that, we can use that as a conversion factor. So we can say how many moles are in 5 grams of carbon. So we have 5 grams of carbon. We want to know how many moles that is. We can use that conversion factor to figure that out by doing that conversion like this. 5 grams of carbon. And we set up a conversion where we go from grams of carbon to moles of carbon. By the way, I should note, the abbreviation for moles is just MOL. It's not much of an abbreviation, but that's what we use, because M is meters and MO is months, so the best you can do is MOL. So how many grams of carbon versus how many moles of carbon? We use this equality here and say, well, there's 12.011 grams of carbon in 1 mole of carbon. And then we can do that calculation just as we did at any other conversion, and say 5 divided by 12.011 is about 0.42. It's about 0.42 moles of carbon. See how that works? So we've got a little less than half a mole in 5 grams. And that we can use then to react it with, or to calculate reactions, sorry. So if we look at these types of reactions, these balanced equations, what these numbers tell us is how many molecules of this one react with how many molecules of that one. But another way to say that is how many moles of this one react with how many moles of that one. And so being able to convert between grams and moles becomes important for figuring out how to set up an equation like this with actual physical quantities that you might measure. So let's look at how we might do that. There's two parts to this. Let's look at an equation, and we can practice balancing the equation too. Cool. Yeah. Again. There's a fancy word for this that you'll probably see in the book. Stoichiometry. That's just a fancy word that means measuring the quantities in chemical reactions. So if we have a reaction, how do we know how much of this thing or how much of that thing we need? We're going to set up a reaction and then do some examples that are really easy and obvious, and then some where we need to actually do calculations to figure it out. So let's look at the reaction between silver and sulfur to make silver sulfide. Okay. Is that reaction balanced? No. How do we balance it? Yeah, we just need to add a 2 here. Okay, we do that. So that tells us for every 2 atoms of silver, we need 1 atom of sulfur, and then we make 1, it's not really a molecule, but we can say 1 molecule of silver sulfide. So let's set up a table that shows that. We're going to say the amount of silver that we have, the amount of sulfur that we have, and the amount of sulfur or silver sulfide that we have. And knowing one of these, we should be able to figure the other one out. So let's start with just looking at it from an atomic standpoint. So we have 2 atoms of Ag. How many atoms of S do we need? 1. That's what the equation tells us. And then how much Ag2S do we get? Careful. It's 1. It's just 1. Because we're looking at the coefficients in the equation, which we didn't write those in, but they're actually 1. So we just copy those directly. 2 of those reacts with 1 of those to make 1 of those. And then this works with moles also. So if instead we had 2 moles of this, we could say, well, then we need 1 mole of this, and we make 1 mole of that. What if we had 2 moles of this one? How much of the first one would we need? 4, right? Because the proportion has to be the same. If one of these needs 2 of these, then 2 of these needs 4 of these, and so on. And how much Ag2S would we make? 2. We keep the same proportions. Great. What if we didn't have such nice numbers? What if we had 1.5 moles of this? How much sulfur would we need? Right, half. And then how much Ag2S would we make? same. So you see how these proportions kind of keep working themselves out here? The proportion is always the same no matter what those numbers look like. And so we could have some crazy number and still figure this out. We could say, well, what if we have 2.54 moles of this? How much of the others would we get? Yeah, we'd have to cut that in half and say 1.27, like that. And now what if that relationship isn't so easy? Like cutting things in half or doubling things is easy to do. What if the relationship is a little bit trickier? Let's try another one and see how we can deal with that. In this case, we're going to react iron with sulfur to make iron 3 sulfide. And I'm sticking with just two things on the left and one on the right, but we could also do this with more complicated reactions, as we'll see in a little bit. Is that balanced? No. How do we balance it? Right. 2 here, 3 there. There. Now that's balanced. So now we can ask the same questions. Yes, if we had 2 moles of this, we need 3 moles of that and 1 mole of that. But what if we didn't have such nice numbers? What do we do then? Let's set up the same kind of table. So if we had 2 moles of this, we could get 3 moles of that and make 1 mole of this. Let's just pick sulfur. Let's say we have one. Let's say we have 1 mole of sulfur. How would we go about figuring out how much of the other ones we would make? It's a little tougher, right, if you're just trying to look at it, because there's 2 and 3 and 1, and it's not as easy. So what you do is you can treat it like another conversion problem, where you look at the difference in the 2 numbers from the equation. So we might write something like this. In a conversion question, we would start with 1 mole of sulfur, and we would want to turn it into moles of something else. Let's say iron. Let's say we're going to look at the iron first. So we would say, okay, what is the relationship between moles of sulfur on the bottom and moles of iron on the top? That should cancel units in moles of sulfur and give us moles of iron. We can get those numbers from the equation. So we just plug in the numbers that we find from the equation. 2 of these to 3 of these. And so then you do that equation and you get 2/3, or about 0.67. And that's how much Fe we would need. So we treat it just like with those other conversion questions, and that helps us find this. Then we can do the same thing with the other one. One mole of this. But this time, we're going to again get rid of moles of S and instead have moles of Fe2S3. And according to the equation, that's 3 of these to 1 of these. Something like that. So using this technique, if you know the quantity, if you have a balanced equation, and you know the quantity of one of the things in the reaction that you want, you can figure out all the other ones just by doing this technique. So let's let's try another one. Let's say I give you 1.234 moles of iron. See if you can fill in what you would need for S and for Fe2S3. So you'll set it up in a similar way, but with different numbers in that conversion. This time starting with the iron and then converting to sulfur to the 2S3. All right, so you get something like 1.851 for this and 0.617 for this one. So let's look at where we got that again. Same type of equation, but now we're starting with the 1.234, and that's iron. It's always good to keep track of your units, make sure you know what you're talking about. And then that's going to get converted by that type of a formula because we want to go to S from Fe. And the equation tells us that that is 2 to 3. So we get that kind of a result. These are called molar ratios, and it's an important part of figuring out how much of a quantity you need in this reaction. The last part of this is to look at the grams as well as the moles. So if we're actually in lab, if we're actually doing a reaction or doing some sort of a procedure where you need to measure out some chemicals, then we're not going to measure in moles because we've already just kind of established that you can't measure things in moles because you can't count that many things. If you had to measure 1 mole of sulfur, that would mean you'd have to count 6.02 times 10 to the 23rd sulfur atoms, and that's impossible. So when we count things or when we measure things in lab, we're going to do it by weighing. We're going to do it by mass or sometimes by volume. So let's say instead of these amounts, let's say we had 10 grams of iron. How would we figure out how much sulfur or iron sulfide we need or make when we're only given grams and when we ultimately want to know the result also in grams? Any ideas? So let's say we had 10 grams of iron. How would we figure out how much of this and how much of this? Yeah, now we can finally use these red numbers on the periodic table. We would use something called the molar mass, which is the mass of 1 mole. Sometimes it's also called the molecular weight. And we find those through the periodic table. So I don't know if anybody noticed, but when we started talking about this today, we mentioned that a mole of carbon atoms weighs 12.011 grams. If you look up at carbon on the periodic table, number 6, you'll see that number in red, 12.011. So every atom on the periodic table, every element, that's its molecular weight. What if you have a quantity like, or a compound like Fe2S3? What do you think you do in that case? That's not on the periodic table, so what do you do? Yeah, you count everything that's in there, exactly. So let's look at both of those. The molecular weight of iron means that 1 mole of iron is 55.8 grams. A mole of sulfur is 32.1 grams. And a mole of iron sulfide is, we're going to take the iron, which is 55.8, and multiply it by 2. And then add that to the sulfur, which is 32.1. And we multiply that by 3, since there's 3 of those in the formula. And we get 207.9. And as with anything else, however many decimal places you want to use, that's kind of up to you. So we'll not be too strict about that. Okay, so now we've found some molar masses from the periodic table. And now, since those are equalities, now we have a relationship between grams and moles. So all the stuff we just did with moles, we can now turn it into grams using this kind of a method. And most people find the easiest way to do it is to string everything together in one big equation, one big conversion equation. So for example, right there, this might look like this. It might look something like this. We'd start with our 10 grams of iron. And then we get a quantity that takes us from grams of iron to moles of iron. That's going to be our molecular weight. We'll fill in the numbers in a minute. Let's get everything set up first. Then we're going to look at something that gets us from moles of iron to moles of, let's say, sulfur. We'll do that one first. And finally, we're going to go from moles of sulfur to grams of sulfur using that molecular weight. So let's fill in those numbers. How many grams of iron are in a mole of iron? Right, 55.8. That's that molar mass. And how many moles of sulfur are in moles of iron? How do we find that? Right, that's going to change based on the equation. In this case, we pull those numbers directly from the equation, and we get 2 of these for 3 of these. And then finally, how do we know how many grams of sulfur and moles of sulfur? Yeah, we'll once again use the molecular weight or the molar mass and say there's 32.1 of these in 1 of these. And once again, our units all work out. So grams of iron cancels with grams of iron. Moles of iron cancels with moles of iron. Moles of sulfur cancels with moles of sulfur, and we're left with grams of sulfur. So we evaluate that expression. going to be 10 divided by 55.8 times 3 divided by 2 times 32.1. And we get 8.63 grams of sulfur. So for every 10 grams of iron, if we want to do this reaction completely, we need 8.63 grams of sulfur. Now see if you can do the same thing and figure out the amount of iron sulfide that we would get at the end. So to do that, you're going to use the exact same expression. The only things that change are this term, because you don't want moles of sulfur, you want moles of Fe2S3, and this term, because you want grams of Fe2S3 and mole of Fe2S3. So try to calculate that out and see what you get. The book while you do that. I'm going to look at one problem from the book here. Okay. All right. So did you get about 18.6? Anybody see a shortcut there? Yeah. So that works, and that's why I asked you to do it that way. This way that we talked about down here always works, and it's always the same. You just change the numbers as you need it. The technique is always the same. But you could also recognize that we have that conservation of mass in a chemical reaction. We can't destroy or create mass. So if we know that one side has 10 grams and 8.63 grams, we could just add that together to get the total mass on the other side. So if there's only one thing in the reaction that you don't know, you can just add and subtract the other ones to get that one. But if you don't want to deal with that, this technique will always work. All right, so the last thing I want to show you kind of what is the end goal to be, what should you be able to do at the end of all this after all our practice in class and your practice at home. And it's something like this. Let's try this one here. And this is why these things are useful and powerful, is that we can look at something like this. When solid lead sulfide, lead 2 sulfide ore, burns in oxygen gas, the products are solid lead 2 oxide and sulfur dioxide gas. So a chemical process is being described. What we should be able to do is first write a balanced equation for this reaction, and then figure out if we want to actually do this reaction, and we want to start with 30 grams of lead 2 sulfide, how much oxygen are we going to need to do that reaction? How much oxygen do we need to add into that? So we've got a little bit of time left. Let's see if we can get a balanced chemical reaction. If you're really fast, see if you could also solve part B. But at least let's try to get that balanced chemical reaction. And then if we don't quite finish it up, we'll pick it up on Thursday. See what you can do there. right, we're almost out of time, so I want to at least give you the equation, and then we'll look at the calculations of this next time. So lead 2 sulfide is going to be PbS. That's a solid. Burning an oxygen gas means reacting with O2 gas and forming solid lead 2 oxide and sulfur dioxide gas. So is that balanced? It's not. It's close, but not close enough. So this one's actually kind of a tricky one to balance, but this is one of those issues where we have to double it, because we see on the right side there are 3 oxygens, on the left side there's 2 oxygens. So that means that we need to have like 1.5 of these, which we can't really have. So we double everything except the oxygen. We go 2, 2, 2. And then we now have 6 oxygen on the right. So we can put a 3 here to get 6 oxygen on the left. And think about all the skills required. Excuse me, is you have to be able to first write the formulas from the names, then put them into an equation form, and balance that equation. And only then can we go on to the next part, which we'll do next time, where we calculate this stuff. So that's why I keep saying, make sure you know the names, make sure you work on your equations. If you can't do that stuff first, then the ratios are going to be all off for the calculation afterwards. So that's really the first step. And then on Thursday, we'll practice this more, and we'll talk about how to apply those to equations like this. So give that a try, and I'll see you tomorrow for lab.